So first, of course, I want to thank the organizer. Thank you, Hung, for giving me the opportunity to speak here. I think it's quite good, actually, in this time that we have to spend home, to have like 3 very good I'm not talking about mine, but at least 2 very good PDE talks today to look at. That's very nice. So the work I'm going to present today is about the derivation of the homogeneous kinetic wave equation, and this is joint work with Germain, who is, okay, so this is a bit bad, Germain, like that, who is at Courant. Okay, so since it's a problem that I wasn't really working in before, I'm a bit new in that kind of stuff, so I'm gonna give a presentation which will be, I hope, nice for people who don't know much about weak wave turbulence. And I'm gonna first start to give what are the main ideas behind the kind of result that we can explain. So my first part of the talk is gonna be about basic stuff on this question. So what's the problem? The problem is the following, is that you start with a dispersive equation. So here I'm dealing with the nonlinear Schrodinger equation, and I'm gonna solve it. So here on the torus, okay? And you see I introduced a parameter lambda. So here I have lambda. What does it mean? It means that my solution U will be in some sense of size 1. So lambda will keep the size of the nonlinearity in my problem. And okay, I will either use this formulation that I write here, which is on, say, the physical side, but I can also work on the Fourier side. So I will use this convention for the Fourier transform. And if I write what my nonlinear Schrodinger equation becomes on the Fourier side, I see this, okay? So what it means is that if I just keep the linear part, my Fourier modes, they just want to oscillate. Their phase is oscillating at speed k square. And if I add the nonlinearity, I will see that the nonlinearity in Fourier is a convolution. So Fourier modes will start to talk to each other. And here I have modulus of u squared times u that I write as u bar u. And here I have Fourier transforms of u bar u. So the problem I want to look at is a bit what I try to put on this picture here. So you see this is the surface of the ocean. So it's an image that I took from the website of a physicist actually working on a weak turbulence problem in wave equations. So what do you see? You see that there is a problem on the whole space and that the solution is rather small, right? And also you see that there is not one big thing to look at. There is not one big wave to look at, but rather there are small waves, and I want to understand these small waves. So it gives a hint that the good framework to study this kind of phenomena is to look at the statistics, actually, of the solution. So I will put a bit of probability in my problem and try to model, even though it's unclear that my nonlinear Schrodinger equation itself is a very good model for this picture here, but this is what you should keep in mind. Small waves, which are exchanging energy in a weakly nonlinear regime, because I will use my parameter lambda to say that, in some sense, my nonlinear effects are small. Don't hesitate to interrupt if you have questions. Okay, so as I said, I want to take a very specific initial datum. So if you look at it, it's better given in Fourier. So in Fourier, what I do is that I take a deterministic function, which is A, which is related to the covariance of my field, and I will multiply it by some random function gk. So what is gk? Gk is a Gaussian. For each k, I pick different Gaussians. What does that mean? It means that I take an initial data which has all its Fourier coefficients taken randomly, and they're taken independently. And gk is centered, so the mean is 0. So you may ask why this very specific initial data. And here is an explanation. So I go back to my picture of the ocean here, and I want to have a problem on the torus, which should, okay, in some sense, look like that. So there is a basic result in a Gaussian field, which says that if you have a Gaussian field, that is to say, if you have a function defined on the whole space Rd, such that when you look at one point in particular, it has a Gaussian law, under some, okay, hypothesis, it can always be written under this form. What it means is that this is a superposition of linear waves, if you want, with dw, which is a linear process. So this is nothing but infinitesimal Gaussians. If I take this function on the whole space, I can compute the key number for this Gaussian field, which is the correlation function. And you see that the correlation function is just my A. Okay? So if I take this formula, this gives me a Gaussian field for which, as soon as 2 points are distant at a distance that is greater than 1, they start to decorrelate. So say the information is almost independent. If I want to have a Gaussian field for which I have an information on correlation which lives at spatial scale epsilon, a small scale, what I do is just that I rescale this formula, and I obtain that. So what I'm saying is that you should look at the drawing I'm doing right now. It's that I have a field which is oscillating very, very fast at scale, so sorry for my drawing, at scale epsilon, and I put it in a torus of size 1. So it's oscillating at a scale which is much smaller than my torus. And if I restrict that to the torus, a good approximation is precisely this, which is my initial data. So this explains why I'm looking at such a particular initial data. I repeat it. It's just that I want, in a way, to approximate a problem which is set on the whole space by a problem on the torus. And I want to have an initial data which is Gaussian, random, and which oscillates very, very fast at scale epsilon, which will be a small parameter. So there is something which is now well known for such field, is that if I take this renormalization, so this is still the same initial data I'm writing here, then in fact, although its support in Fourier is very big, of size epsilon minus 1, in fact, any LP norm will remain of size 1. What it means is that, okay, my solution is very, very high frequency. However, each linear wave on the torus, representing in Fourier my function, is independent of the other because the Gaussians are taken to be independent. So there are many cancellations, and in average, my function is of size 1, but oscillating very fast. So now that I've said that, I've introduced you to the two main parameters for this so-called weakly nonlinear problem. So one first parameter was epsilon, the Fourier size of my solution, and it gives me my first time, which is the linear time, epsilon square. What does that mean? It means that if I wait a time of order epsilon square, then I will see some linear change, because my linear dynamics is just this. My Fourier coefficients are oscillating at speed k square, and since k is of order epsilon minus 1, it's oscillating very, very fast. I have another time scale, which is that of the nonlinearity. I've convinced you above that my solution is roughly of size 1. So if I solve a nonlinear problem like this with u of size 1, then it is true that I will only see some change if I wait a time which is lambda to the power minus 2. So you see, since I have two parameters, there are two typical time for the linear dynamics and the nonlinear dynamics. And saying that we are in a weakly nonlinear regime amounts just to say that my linear time is much more smaller than the nonlinear time. And then what's the picture to keep in mind? you will have a dynamic which will be, to leading order, linear. But weak turbulence aims at finding what are the nonlinear effects. But since the linear effects are acting at a time scale which is way smaller than that of the nonlinear effects, what happens? Your nonlinear effects, they accumulate over time, little by little, but each time they are in a way degraded, they are attacked by the linear effects. So you have a linear filtering of your nonlinear effects. This is what I put here. And so the main problem, now that I've introduced you to my equation and my initial data, is the following. Can I say how the statistics of my data will evolve? So I give you my Fourier coefficients and I give you their statistics initially. Can you say something about their statistics at some later time? And can you say that maybe if you weight some typical size that we will see up here later on, then you start to see your Fourier modes actually exchanging really information and you see something statistically. Okay, at the mathematical level, what it means is that I will solve an NLS equation. Maybe not all of you are very familiar with that, but now it's well known how to treat this equation in many cases. But I will solve it with two parameters in an asymptotic regime. I will have epsilon that goes to 0. My solution will be very, very singular, oscillating very fast. And I will have a nonlinear effect which will be kept small. Okay, so let's go. If you want to understand what will happen, there is something that physicists do to derive my limiting equation. It's just to study quasi-solutions. So as I was saying, my aim here is to give you the basic ideas about what are the key tools to try to attack these problems. And quasi-solutions, here I will give you all the main ideas about my main theorem after. And with the quasi-solution, I will give you a formal derivation of what I expect to see for this equation. So, what is a quasi-solution? As I was saying, to leading order, my dynamic is linear. So, I will treat the nonlinear terms perturbatively. If I do so, I can use Duhamel formula. So, if I solve a forced Schrodinger equation, then I obtain this for the solution. Now let's see. I want my solution at leading order maybe to be just the free evolution because my nonlinear effects, they are small. So I will say that my first approximation is just U0, which is the free evolution. Okay, it's given by an explicit formula. Then, if this is to leading order my solution, what will be the next nonlinear effect? Well, this will be the nonlinear effect created by this first order approximation. So I'm doing an iteration of Duhamel formula, a kind of Banach-Picard iteration. And so I will add a correction U1, and U1 will solve a Schrodinger equation with forcing being the one created by U0. I have a formula for U1. U1 is just a Duhamel formula, and I put inside the linear evolution of my initial data. And I keep doing this way. So I will introduce now U2. U2, well, it takes into account the nonlinear effects created by U1. So U2 will solve this equation. And I will stop here for the formal derivation. Later on, I will include more terms in my quasi-solution. And you see that, well, U0, it's easy to write down a formula. U1, it's okay, is U2. U2, it starts to be a bit big, right? And if you want to go up to n times this operation, it would be a bit big. So what is the main philosophy behind the derivation of my effective equation that I will present later on? It's the following. Is that, in fact, if you just do local well-posedness, you know your iteration of Duhamel formula done this way will converge for some small time. But maybe, given that I'm choosing a very particular initial data, maybe it will converge in a very bigger time scale. And maybe it will live much longer. And maybe too, with my iteration of the UML formula, I will be able to compute what are the main nonlinear effects. Okay. So now, what are the key things to understand quasi-solutions? So as I was saying, if you are iterating your UML formula, your formulas, they are becoming uglier and uglier. So you can just do a little drawing to represent what you are doing. So I recall to you the formula for U1. U1 is just what sees the nonlinear effects created by your free evolution of the initial data. So you see that what I'm doing is that I'm taking U0, making a free evolution, and doing that for 3 terms. This I represent this way. I put some edges which are going up and which represent free evolution of my initial data. Then, at some point, I make the product of these 3 things, and I make some linear evolution again. So I will put a vertex when I merge these 3 linear evolution, and then I put some edge to say that I'm doing free evolution again. Okay, so this I can do to any order, and what I'm saying is that when I iterate my UML formula, I can do drawings to say what I'm doing and which was my iteration. There is something else to understand quasi-solution. As I was saying, your initial data, each Fourier coefficient is taken randomly according to some Gaussian law. So you need to understand a bit more of Gaussian variables. So here, I'm putting back something which is well known on Gaussian variables, which is Wick formula. What it's saying is that if you want to know the expectation of a product of an arbitrary number of Gaussian variables, you only need to know the expectation of the product of them 2 by 2, okay? And here, what you're seeing is that if I'm writing you the example of 4 Gaussian variables, in fact, there are 3 terms in the right-hand side, whether I was putting x1 and x2 together and then x3 and x4 together, which is my first term, or whether I was putting x1 with x3, x2 with x4, or whether I was putting x1 with x4 and x2 with x3, which is my last term. So if you want, here I was just putting the example if I take 4 Gaussian variables, but there is a generalization of that, which is that the expectation of a product of Gaussian variables is just the sum over all possible ways to put them together 2 by 2 of the expectations of the product of just 2. Okay, so this is a well-known formula. It's called Wick formula, proved by Isserlis at the beginning of the 20th century. And I give you an application because if you remember, my initial data, it's of this form. I'm taking a Gaussian variable which are independent at each different coefficient. So as a consequence, since they are independent, whenever I take the expectation of a product of 2 different, it's 0. So what it's saying is that if I apply the formula that I was writing above, when I'm taking the product of 4 of these terms, computed at K1, K2, K3, K4, in fact, most of the time it's 0. So most of the time, in expectation, if I multiply my Fourier coefficients with others, then it gives 0, unless I had that they were equal 2 by 2. So you see, it's not 0, only if maybe K1 was equal to K3 and K2 was equal to K4, or K1 was equal to K4 and K2 was equal to K3. So if you want, going back to my problem, I have many Gaussian variables, and I want to understand how product of them will behave. What I'm saying here is that there is formula to do computation, and you can expect many cancellations. So I give you a quick application of that. If I want to compute the L4 norm of my initial data, I told you earlier that this should be of size 1. To compute it, I can just express how to compute an L4 norm in Fourier. And then I use what I was telling you about the expectation of the product of Gaussian variables. If I do that, what I see is the following, is that I was seeing a convolution involving a certain number of variables here. And when I take the expectation, only when wave numbers were equal 2 by 2, maybe this term wasn't 0. So if you want, there was some quantity which was computed on some very large domain of R3 here, and then it forces a cancellation. So in fact, I reduce the dimensionality, and if I do the computation, I find that this, in the end, is Grantot of 1. But if I was only using an inequality, say Bernstein inequality, since the support of my initial data was of size epsilon minus 1, I was predicting that it was huge in L4, but this is not the case, and I have to really use the fact that I'm using Gaussian random variables. Okay, so there is a last thing that I need to tell you to understand what's going on for my problem. This is resonance. So I recall you the formula for U1. U1 is just, I accumulate the nonlinear effects created by my linear dynamics. And if I do that, I can put it under this form. You see, there was a temporal oscillation that I can put in a short way like this. And here, I have to integrate from 0 to t some e to the power I omega s. If I do that, this term here, it can be either of size t, when my resonance moduli omega is small, or if it wasn't small, then it's of size 1 over omega. So what it's saying is that when I'm integrating over time this oscillatory phase, then the main part of the information will be when omega is very small. And the nonlinear effects, they will accumulate near the set omega equals 0. So if I say back what I was doing earlier, I want to see that there is, to leading order, some dynamics which is linear, and that the nonlinear effects, they accumulate, but they are attacked by the linear dynamics. So in fact, the only thing that I will see of my nonlinear effects later on will be what was near this set, the resonance set omega equal to 0. Okay. And you see here, for example, I put you some typical technical lemma that we are using in the paper, is that if you're working on the torus, then you can precisely count what are the possible wave numbers such that this modulus of resonance satisfies the smallness condition, and such that you have some nonlinear growth. Okay, you can compute that explicitly. And you see that there is something very particular, that you have to remain with times being less than 1, because if you go for times bigger than 1, then you start to lose what we call equidistribution, and you cannot approximate your problem with the continuum. Okay, so now I've explained to you the 3 main things: how I can do Feynman diagrams to iterate my Duhamel formula, how I can use Wick pairing and Wick formula to know how my Gaussians are behaving when I multiply them, and I've explained to you how I can compute my resonance in my formulas. One first thing that I need to do is to tell you what is the leading nonlinear effect. And this is called Wick renormalization. So if you want, if I take my initial data, which was very specific, and if I want to compute formally what it looks like my nonlinearity, so u square u, then I can do this. I can try to estimate it when I hit another Gaussian field V. And there is some formula, which is really due to the fact that it's a Gaussian field. In fact, it behaves like the L2 norm of u times u. So what it's saying here, it's a little computation using what I introduced before that says that, in fact, my nonlinear effects to leading order, they're just equal to the L2 norm of my solution times U. However, this is a conserved quantity for my flow. So the L2 norm remains constant. So if you want, the nonlinear effect to leading order is just a constant times U. So if I solve this equation, when I replace the nonlinear effects by their leading order approximation, then I don't see anything in particular because this is a linear term in U, if you want. And what I see is just some oscillation, which is with the typical scale of time being my nonlinear time scale that I introduced earlier. And so, in particular, if I take a solution and I just do linear evolution and I change the phase, the statistics remain unchanged. So I don't see what the nonlinear effects did to my statistics at this moment. So what it's saying is that this first effect of the nonlinearity wasn't doing anything for the statistics at all, and I need to remove it. How to remove it? I just renormalize my solution. And if you want, the correct problem I will look at is rather this equation, where I remove this L2 norm of the solution, which is constant, but this is the good way, if you want, to see the next order nonlinear effects. Okay. What I'm saying in these slides is just that before I was using a quasi solution and I was expanding my solution doing Feynman diagrams. Now I was cheating a little bit because I was not telling you that I would do some Vic renormalization later on. What I'm saying here is that, in fact, I can keep the same drawing. So in particular, for U1, even though now I need to remove some partial expectation in the formula, I will keep the same drawing, saying that U1 is just 3 times my linear evolution that I make interact, and then that I may follow my linear dynamics again. Okay, so I hope that I gave you all a hint of what a quasi solution is, why I need to renormalize to take out the first nonlinear effects which are not interesting. And now I'm just summing up what I said. I will take a quasi solution of this form to understand my dynamics. What I'm doing is just iterating Duhamel formula. I can represent UN with a Feynman diagram, so I do little drawings to expand my solution. And what is UN? The Feynman diagram, there is a formula for it. It's a bit long, and it involves an integral in a very high dimension. I have many products of Gaussian variables, and I have a large number of oscillatory phases. My oscillations, they concentrate the information on specific sets called the resonance set, where the omegas, the resonance moduli are 0. And if I look at the statistics, well, many of the Gaussians, when you take the expectation, they will give zeros. You will have many constellations due to the particular structure of my problem. So now we have all the tools, and I can give you a little computation to say what we can expect for such solutions. So my third part of my talk will concern how I can compute the statistics of my quasi-solution that I was introducing. So now I will use all the little drawings that I explained to you. So I said that U was equal to U0 plus U1 plus U2. Very well. I told you that I have drawings to expand U. So this is U0, this is U1, and when I expand my Duhamel formula, U2, I can have 3 possible terms. Now there are some symmetries in my graphs, and so if I take them into account, I obtain this formula here. Okay, so I have a graphical way to represent my expansion, and if I want to compute the statistics, so what is the expectation of a Fourier coefficient at some later time? Well, I just need to compute the expectation of this here that I can expand and distribute the product. And to do so, I will do the pairings that I introduced before. So remember that U0 is just a straight arrow. U1 is just 3 arrows that I continue after. If I compute the expectation, I said that due to the Gaussian variables in my initial data, the initial frequencies, they needed to be equal pairwise in order to give a non-zero contribution. So whenever they are equal pairwise, I put something like this below. This is how you compute using Feynman diagrams. So here, I'm identifying these variables here. And there is another term, which is the one on the right. However, one effect of the Vic renormalization that I introduced before is that these terms, they were actually removed. You remember in U1, I was taking out some partial expectation, and this has the effect of dropping all terms which looks like that. So you see, what I'm trying to say to you here is that you have some just symbolic way to compute stuff out of Feynman diagrams. And in fact, if I want to compute this, how my first nonlinear effects will change my statistics, well, it's 0. So, okay. Now I can move to the other term. I have this formula that I'm putting on the board. So if you want to compute this expectation here of my first nonlinear effects, well, you do this as a diagram. So I put U1 on the left, U1 on the right. I do the pairing of my initial frequencies here, and I have different ways of doing the pairing given by Vic formula. I remove all of them which were taken out by Vic renormalization, and so again, I have some symbolic computation that tells me that this quantity here, I can just represent it by some drawing. So I'm hiding completely what the actual formula here, but okay, I can do drawings like this. If I do many drawings, in the end, I have this. So the expectation of my Fourier coefficient at some later time, I just need to compute this. So I see the initial data, this is the first term, and my correction is just given by some Feynman diagrams. There is a way to go back to an actual formula. If you do so, you end up with that. And here, it's very important to see what I will do. This formula here exactly corresponds to my drawing here, okay? And so this formula, what it is saying is that at some later time, the nonlinear effects, what they produced was some collision type kernel here. I have some product of my initial A's. What is TNL here? TNL is the nonlinear time. Yeah. There was a question by Yudeng. So TNL, here it's my nonlinear time. So I'm taking a nonlinear time, which is much smaller than some time that will appear, the kinetic time. Okay. And so, okay, I go back to what I was saying. This is the formula that I compute out of my quasi solution. And what I see is that there is a sum corresponding to some convolution in Fourier of my nonlinearity. And there is some integral time of an oscillatory phase, which corresponds to the fact that I have my linear dynamics, which is filtering my nonlinear effects. I do two things. I do some continuum approximation. I replace the sum by an integral, and I do a stationary phase to keep only the important part of this oscillatory integral here, and I end up with this formula. So what it's saying is that at some later time, the first correction is this, of this form. And you see that in front, I have a factor t over lambda minus 4 epsilon minus 2. And so what it's saying is that the new nonlinear effects that will change my statistics, they appear with some typical time that is precisely this thing here. And in the regime that I was describing, the weakly nonlinear regime, you can check that this is way after the linear dynamics and the nonlinear dynamics timescale. Okay, so to sum up, I expand my initial data using Duhamel formula. I can do little drawings, which are Feynman diagrams. I can do computation of them. Then I go back to some real formulas. And what I see is that, in fact, what will appear with the nonlinear effects is just some kernel here. And the conjecture is the following, is that in some asymptotic regime, as epsilon goes to 0, as I'm weakly nonlinear, we conjecture that statistically, your Fourier coefficient, they will evolve according to the so-called kinetic wave equation that I write here, which is just to say that with this new time scale, the evolution is encoded by some collision operator that is written here. So this was a very long introduction, but at least I gave you all the tools that I will use later on as well to say to you that I want to derive this equation. This is an effective equation, and for this very specific initial data for my Schrodinger equation, I expect that this will encode my statistics. So the theorem I will give right now before giving some references. So who was working on this problem? So in fact, this is a problem which has a long history in physics. So the first things, they go back all the way to the 20s. So Peierls was doing some quantum physics, and this was appearing in quantum physics. Hasselmann was doing fluid dynamics. Then the theory was revived by Zakharov, Lvov, and Falkovich, among others. And why there are so many people in so many different fields? It's because, you see, in fact, all that I need is that I have some linear Hamiltonian that I perturb by some nonlinear dynamics, which are of a smaller order. And if I add to that some randomness in my problem, maybe the nonlinear dynamics, I will see some effective equation capturing them statistically. So the derivation that I was presenting to you of the kinetic wave equation from quasi solution, you can find that in classical textbooks on this field. So what about now rigorous math? So here, unfortunately, I cannot put all the names behind that, but there was some early work by De Suzony and Zvetkov, studying correlations for a similar dispersive equation. Then there was some work last year by Buckmaster, Germain, Annie, Chata, who obtained the validity of this kinetic equation and the existence of the solution at a non-trivial time scale. There was some work by Dimov and Kuxin, because this problem can also appear when you force randomly your equation. So this appeared this summer. And very recently, by Yudeng, who was asking the question before, and Zahir, there was a simultaneous result to ours, in which they proved that in some regimes, particular regimes, maybe I will have time to comment on that, well, you can prove that your solution will live until a very big time, almost reaching the kinetic time, the time at which you can see statistically some nonlinear change, up to an arbitrary polynomial loss, which is it's the first time that it was shown in this problem. Okay, so this is about the derivation, but now what about the tools that we are using? So mainly we're using some tools developed by Bourgain. So for example, the use of Bourgain spaces to control the solution, and also in his work on invariant measures for dispersive equations, Bourgain was already using the fact that you can use these many constellations for Gaussian initial data to actually prove improved nonlinear bounds. So we use that a lot. Then for the Feynman diagrams, there was some very important paper by Lukainen and Spohn, who did the analysis of them in some weakly nonlinear regime as well. And finally, Zvetkov, for the wave equation, they built on the work of Bourgain and also showed how you can control your solution if you have some Gaussian initial data. So in the present work, if I want to tell you what is new, then this is the following. So before it was not, the kinetic time was not reached. So here we can reach the kinetic time up to a arbitrarily small, okay, so I forgot to put it here, but this polynomial loss is arbitrarily small. So we can almost reach the kinetic time. And then I think Feynman diagrams, they were not used so much to compute nonlinear quantities for nonlinear analysis. For example, we use Feynman diagrams to compute the linear stability of our quasi solution. We use them to compute various nonlinear bounds, etc. And what we hope is that since we're understanding better and better our solution, maybe in some future, we will be able to identify what are the enemies or allies in this problem, because we are not reaching the kinetic time in every configuration. And what we believe is that maybe it's false in some configurations, but this would be interesting to investigate as well. So what's the theorem? The theorem is the following. So I take a specific dependence between my nonlinearity and my parameter epsilon, which is the localization of Fourier of my solution. And I can do the following. I can make my solution exist on an interval 0, 1. So in this problem, it's already non-trivial because my nonlinear time is way smaller than that. It's much more smaller than 1. So if you want, the first result is that we can control the solution on a non-trivial time scale. And on this non-trivial time scale, we can prove the validity of the kinetic wave equation according to this. It's that if you compare the statistics of your solution to that predicted by the kinetic wave equation, if you just take the Taylor expansion at time 0, well, the correction will be of even smaller order. So if you want, this is a way to justify not fully the kinetic equation over the full kinetic time range, but rather to justify the very beginning of the kinetic behavior for this equation.
What is new? What is new?
What is new? Yeah. So here, these are just some smallness parameter. So if you want, epsilon to the power nu, nu is anything which is, I mean, in the end, it's very small, but it means that this is of polynomial size better in epsilon than the correction that I see here. This is what it means, epsilon to the power nu. Okay? Okay. So now, so Hung, at which time can I, how much time do I have for the proof now?
You can have 5 minutes.
5 minutes, okay. So then for the proof, I will just move to the linear analysis. I mean, I will do the sketch of the proof first. So as I was explaining to you, what I'm doing is that I'm taking a quasi solution of a very high order here. The same that I was using some little drawings to express. And then since it's not a true solution, I have an error. And I need to control the error. The equation for the error, classically, is just that I see some linear evolution. Then I see some linear terms when my solution is, my error is interacting with the approximate solutions, and bilinear, trilinear, and remainder terms here. Okay, so all these terms, they need to be controlled. And since I just have 5 minutes, I want to explain to you why the interaction with my error term and the approximate solution, so why, if I just keep this part of the equation here, the linear part, I can control it. Okay, so here, I write to you my linearized problem. Philosophically, what is the problem? The problem is that my approximate solution, it's a different one each time I'm taking a different element in my probability space. So for each realization, I have a different approximate solution. So my linearized dynamics depends on probability. What I put here as LUR is actually changing each time I take a different realization. So, okay, this is one first thing. Then the second thing is that if you're solving a Schrodinger equation, then you can control it in Bourgain spaces. So I don't have time to explain exactly what they are. And controlling the effects on Bourgain spaces, well, you just have to compute some norm of this product in a Bourgain spaces where you just modify the indices. You see here I was at B, and now I'm going at B minus 1. Okay, so what I need to do is just to study such products in Bourgain spaces. Moreover, since my solution, the approximate solution, is something at scale epsilon minus 1, then it will only move my information on UR also at scale epsilon minus 1. So I can further restrict the study of my linearized dynamics on cubes of size epsilon minus 1. And if I do so, I can represent this using Feynman diagrams. This is W, this is the app bar, and this is the app here. And you see that, okay, it's just a little drawing, but in fact, understanding a linear dynamics amounts just to understand what happens when I make W hit against 2 times my approximate solution. I can use my Feynman diagrams as before, some random matrix tools, and in fact, compute it as evaluating the trace of this big thing, which is nothing but the trace of a gigantic matrix. And if I can compute that, this will bound my linearized term. So yeah, I didn't have time to go much more in details for that, but to sum up, yeah, okay, I will stop here.
Okay, you have 5 minutes.
I have 5 minutes?
Yeah.
Okay, so I'll go a bit more in details now. So, okay, as I was saying, you see here, this is my nonlinear term, my linear term, sorry. Since V app is my approximate solution, I have terms of the form V app bar that I put like this. This is V app bar, this is V app, and W. I make them interact, and then I put a linear evolution like that, which is reflected in the fact that I'm taking an indice here on my Bourgain space that is minus 1. I put further a restriction on the localization in Fourier, which is that I just restrict on a cuboid of size epsilon minus 1. If I do that, then I have some linearized term. What I'm saying is that this, since it depends on probability, I can only maybe control on some large set in probability. And the proposition is the following, is that if I want to solve this linearized dynamics, I can do this on a set of almost measure 1. Why? Because this part here, I can treat it perturbatively. The linear effects are in fact of order 1 over my kinetic time, which is very big for my problem. And so if you want, the linear effects, they are with a constant which is much more smaller than 1. So I can swallow them and do a fixed point argument and prove that the solution of this linear problem here enjoys the same bound as the solution of the problem if I didn't have my linear term. Okay. And so, okay, since I have 3 minutes more, what is the idea for that? So as I was telling you, if I look at the Fourier coefficient of my solution, they are changed because of the linear term. And I can see that as a matrix because Fourier coefficients, they live in Z to the power D. I restrict them on some cuboid of size epsilon minus 1. So it's just a huge vector, and I'm doing some linear operation on that. So my linear term, it's just some very big matrix with many entries. How do I estimate the operator norm of a very large and random matrix? Well, if you want to estimate the operator norm of a matrix M, you can translate this problem into estimating the operator norm of a positive matrix just by multiplying M by M star. And you can also put M by M star to some power N and obtain this formula, and this will be still true. Okay, so first, I reduce my problem to that of finding the eigenvalues of a self-adjoint operator. And then, since I'm symmetric and non-negative definite, estimating my norm can be done by estimating the trace. So the norm, if you want, it's the biggest eigenvalue, but I have no idea about what are the eigenvalues of this big matrix. But I can compute the trace, and I obtain this formula here. So there is a way to estimate the operator norm of my big matrix just by estimating the trace of MM star to some very large power. And now this is the drawing that I'm saying. This is M, this is M star. I repeat the operation to an arbitrary number of time. This is M star. And this whole quantity here, I put this relation like that to say that I identify my input and my output, which is the fact that I really compute just some trace. So there is a very complicated Feynman diagrams here because everything is hidden also below. But this big Feynman diagram actually computes my linearized operator norm. And I've explained to you how I can compute stuff out of Feynman diagrams. So this is one example of how to use Feynman diagram to do linear analysis, for example. So you can not only compute the statistics of the solution, but also compute, for example, linear stability with Feynman diagrams. And now I can stop. And thank you very much for your attention.